Thank you all for coming to our session today. I hope you had lunch and loads of coffee because we really don't want this session to turn into a cure for your insomnia. So thanks for coming. A little bit about ourselves. My name is Jules Damji. I am the developer advocate at Databricks and also the program chair. So on behalf of Databricks, I want to welcome to the summit as well, for those of you who have crossed oceans and lands. And a little bit of my background, I worked as a software engineer at some of the companies. And here's my esteemed colleague, Brooke, who's going to introduce herself and then get us started, at least in the first half of the presentation, and then we'll sort of change back and forth. Brooke?
Thank you, Jules. Hi, everyone. My name is Brooke. I'm a data scientist at Databricks, as well as a data science instructor. So this is the agenda for today's talk. We're going to talk about the impact of big data and how it's permeated our lives. And then we're going to survey 3 different deep learning frameworks. We're going to start with TensorFlow and Keras, then switch into the distributed setting and talk about deep learning pipelines and transfer learning. Then we'll do a very fun demo, and at the end, we'll try to have a few minutes for Q&A. So what has big data done to us? Machine learning is everywhere, from the movies that you watch on Netflix, to the products that you buy on Amazon, to facial recognition. But the hardest part of AI isn't AI, it's the data. So this is from the Hidden Technical Debt in Machine Learning Systems that Google published as part of NIPS 2015. Each of these rectangles roughly corresponds to how much time Google spends on each of these tasks for their AI systems. And you'll notice here that the machine learning is a very small part of their entire AI ecosystem. And so this is the motivation for Apache Spark. So as you saw in the keynotes earlier today, Apache Spark is the first unified analytics engine. It uniquely combines big data processing, your ETL workloads, your SQL, your streaming, and machine learning libraries. And with that, I'd like to hand it over to Jules, and he'll start off with introducing TensorFlow and Keras, and then we'll switch back and we'll talk about deep learning pipelines.
Oh, thank you, Chris. Now, this morning you actually attended the talk, and there was this dilemma among data scientists and data engineers, or which zoo of the frameworks that you actually choose from. What are the criteria as a developer, those of you in the room, would choose to see which are the best 3 learning deep pipelines that I should choose? Why should I use them? What should I use them? What programming language should I use? And there is a whole bunch of them. So what I'm going to talk about today is we decided to choose 3 deep learning pipelines which are quite popular, and I'm going to give you the reasons why at a very high level, at a very conceptual level. So we'll start with TensorFlow. What is TensorFlow? It's actually open source by Google in 2015, but the framework was actually created with 2 propositions in mind. One was that internally they wanted to use that particular framework to do all the machine learning and all the deep learning and all the AI applications using particular TensorFlow. And the second requirement was that they wanted to have it at a very low level, so it would allow them to do very numerically highly intensive mathematical computations, because if you look at all the machine learning algorithms, they have a very strong numerical component, and they wanted to have the ability to actually run on multiple architecture, including the GPUs, which are dedicated to a lot of numerical computations, such as graphics, multiplication, and so forth. So they wrote it in C++ as a backend, and that was sort of the primary reason for that actually motivation. But one of the interesting part about TensorFlow is ability to actually express your computations in what they call data flow graphs. And data flow graphs are nothing very similar to what you guys are actually familiar with in Spark called DAGs, which are directed acyclic graphs that have the ability to actually execute either lazily or when you actually perform an action. So you can think of those nodes of a TensorFlow graph as a unit of execution where you can actually specify a function, or you can specify an optimizer, or you can specify an activation function, or any of the numerical computation you want to do, you can express that particular mathematical function in a particular node. And the edges are nothing but tensors, which are data in which they actually go from one node to the other one. And those are represented as metrics, or 1 dimension, or 2 dimension, or n dimension. And that lends its very self to be able to actually represent images, or sound waves, or time series in what they call tensors of different rank. And there are 2 ways in TensorFlow actually does execution. One is called the lazy execution, which is very similar to some of you actually familiar with in Spark. When you execute a particular action, your entire DAG gets executed across the framework. And more recently, in 1.7, they introduced this notion of eager execution, which is something that we as developers are very much used to doing it, which is imperative programming. We come from the imperative programming where we look at a programming language in a procedural way and then we step through that. And that, the ability to transfer from something that I get executed, distributed across your cluster, you be able to actually do it step by step. And that makes the ability to actually write deep learning applications easily for developers to get started so they can step through the particular code. Another important feature that has evolved over a period of a couple of years is that they have a very flexible programming stack right from the low level all the way up to the top. As I said earlier, the proposition of TensorFlow was to be able to actually do these very complex numerical computations at a very low layer. So you can actually run your TensorFlow applications on any of these architectures by the TensorFlow engines, from CPU all the way to Raspberry 32. I've seen demos of that actually show where they're running deep learning applications on that. As you move up the stack, you can actually see the programming libraries become low level, and they have the Python bindings as well, along with the C++ and Java and Go. And more recently, they actually announced that you can actually do deep learning in JavaScript as well. So those of you who are JavaScript friends, you can actually use TensorFlow to do write your applications, and Swift as well, which is one of the things that you actually do in iOS. Now, over the years, they begin to realize that the API was very low level, so they started building layers on top of that. So these layers called data sets and metrics and Keras models are layers that allow you to sort of ingest data very easily, load images very easily, convert your images from that to tensor NumPy arrays so they can be actually used at computers. And as you go up this level, you actually have this estimators called high-level functions, which are straight off the box. So you can use logistic regression, you can use random forest, you can use HD boosters. All those are the sort of high-level APIs. So you can go from very low level, if you're one of those guys who love getting close to the middle, to a little bit of high level. And this actually evolved over a period of the last 4 or 5 years. And now you actually have the entire stack, which is actually quite flexible. And so depending on what your comfort level is, you can actually start working on that. Now the question is this is what it's all about, but why? Why would you actually want to use it, right? And I think that there are 3 things, me as a developer advocate, that I really evaluate whenever I look at a new platform, wherever I look at a new API, or wherever I look at any new programming language. I ask 3 things, right? 3 imperatives, which are very important for any developer. One is there a large community, right? Is there a large community that I can actually connect to, that I can talk to without having the psychological fear or intimidation? Can I actually go anywhere on the online and talk to some of the guys who are actually working on it? And the answer is yes, right? There is a large TensorFlow community of almost 1,400 contributors and almost 11 million downloads. There's no question about that. Second, are the APIs intuitive? Are there loads and loads of code examples that I can actually go to? Can I talk to someone in the community? Now, how many of you over here, including Brooke, how many of you over here who have run that particular program and you got a stack, you got a Java exception or you got a Python exception and you couldn't find out what it is all about? You took that, did a cut and paste, and you went to Stack Overflow. How many of you have done that? Good majority. Why did you do that? Because somebody out there, a guy or a girl, who will respond in a genuine, authentic manner without her ego being on mind. He or she really wants to help you. And that's the power of community, and that's the power why you actually want to use a platform, is because of the actually community. Second, code example. Loads and loads of code example, loads and loads of documentation. And I think that's fairly important. So the second reason. The third reason, obviously, is documentation. I can actually go out there and find out how something is actually done. And if I don't understand documentation, where do I go? What's the ultimate source of truth in this world? Don't give me any biblical connotation. What's the ultimate source? Source. You go to GitHub and you look at the bloody source and you know that that's what it is about. So I think those are actually 3 things. And that's why you actually want to use any platform, whether it's Apache Spark, whether it's Keras, whether it's Kafka. It is open source. There's a large community around it. There are loads of people out there. There are loads of code examples. If I'm stuck at somewhere, I can actually just post something virtually, and someone, some good Samaritan will actually give me the particular response. And it's actually a good way to get started without being completely intimidated. So those are the reasons why you actually want to use TensorFlow, because of the community. Another interesting thing, and those of you who actually are writing distributed computing or writing distributed programs or writing multi-threaded programs have run into the problems of how do you debug something, right? Whether you're doing debugging of a multi-threaded program on a single node or whether you're doing it on a cluster. And that's actually quite difficult to actually do it. But TensorBoard is a visualization tool for TensorFlow that allows you the ability to see how your DAG or how your flow is being executed across a cluster. You can actually go into the particular node to see what the tensor diagrams are coming in, what is your input data, what is your output data, how it's actually being computed, and how it's actually connected. That's just one aspect of it where you can actually visualize your graph after your application has been executed in a lazy way where you can actually look at it. Another thing you can actually do is you can actually write all the summary statistics on file or on log, where you can actually look at your loss function, you can look at your accuracy, how your accuracy actually has diminished, or how accuracy has reached your accuracy level 1 when you're actually doing a lot of training. So these are the tools that actually give you the ability to do a lot of experimental work quite fast. So these are a couple of links over here for TensorBoard. I urge you to actually look at it. It's a great explanation to how you can actually use the APIs within your application to log this data. So you can use TensorBoard to look at your accuracy charts, you can look at your loss charts, you can look at your graphs as well. You can also use that with eager execution. There's a very easy way to enable eager execution in your application by just one configuration argument called tconfig enable lazy execution. And what it will do is, as it actually executes, it will load that particular graph into the file, and you can actually look at as if you're doing step by debugging. So this is actually an incredible tool that the community and the good guys at Google have actually contributed. Another thing that's actually has been released is, as you heard today in Matej's talk about MLflow, is the need to actually productionize models. The need to actually create experiment potential, the need to be able to actually look at things as new data comes in, can I actually train it, and can I redeploy my model? And TensorFlow has that entire infrastructure that allows you to actually serve models, which are in real time, but also update models in real time, and then deploy them in any of the architectures that I talked about at a very low level, where you can actually deploy those things. And you can actually do that in an incremental fashion. And these are some of the great things that have come out from the open source community that has really enabled people like us in this particular room, who are die-hard developers, who actually want to do things like that easily, quickly, and in a manner that we can actually are productive. Now, the question you might ask, and Brooke always asks me every time I work with her, all right, so what? Right? It's one of those typical questions you ask all the time, so what? I get it, Jules, you told me all about it, but what are the things you haven't told me? Now, there is a steep learning curve, right? Because the proposition on which this particular framework was developed, that we wanted to do numerical computing at a very low level and then work our way up. So there is a steep learning curve, but it's very powerful. It's just like Spark RDD APIs gives you a very low level functionality to do what you actually want to do. I mean, how you want to do something, but not necessarily what. So there is a steep learning curve, no question about that, but it is powerful. It's a low level APIs, but it offers control, right? And those of us who are control freaks, this is brilliant. It presumes that you are a machine learning expert. There's no question. I won't lie about it. It assumes that you know a lot of deep machine learning concepts, but there's nothing wrong with that. Right? You just learn. Machine learning is a hot subject, it's a hot topic, and I would urge you to actually pick up a machine learning book and learn about it. But here's the consolation. The consolation is that as you saw the stack, as you go up the stack, it becomes a little easier to do. And they have these estimators, which are high-level APIs, which allow you to do a high-level stuff. But here's the most important part. Keras now is the important integration that allows people who are coming, who don't know TensorFlow, can actually get started easily, which actually leads me to the second one. Why Keras? Why Keras? Again, it's an open source API written in Python exclusively for deep learning. It was written, the current version is 2.1, written by François Cholat, who works at Google right now. It's an API spec. What do I mean by API spec? It means that you actually write to a spec and you can support multiple backends. So currently, TensorFlow is the most popular one, but you can have it on CNTK, you can actually have it in Theano, you can have it in any of the application or any of the integration people actually write to a spec. It's like JVM is a spec, right? When Sun produced that, it was actually spec, and people wrote their JVMs based on the specs. You can actually run on any architecture. Similar idea, it's a spec, and you write the implementation underneath, and you can run it. And if you're running it, it supports multiple architecture. Here's the most important part, the emphasis for the developer. It is a highly declarative APIs. And I like to use the analogy between RDD and frames, or data frames. Data frames and data sets are highly declarative APIs that makes your code look a lot easier to read, and it actually tells what you're trying to do rather than how you're trying to do. So the emphasis is really on the developer. And it is very good at fast experimentation. So because of the fact that you can actually quickly, declaratively tell something what to be done, you can experiment very easily. And you heard today Matej saying about experimentation is an integral part of the development life cycle, and this gives you the catalyst to do things really fast. And like the TensorFlow, it has the high-level programming stack. It's an API spec, and underneath you can actually have multiple engines which are actually implemented, including Theano, including CNTK, and any other thing that you actually want to do. And TensorFlow Keras is the default one. And if you're running on TensorFlow, you can actually deploy it across all this different architecture. Again, why? The question of why comes up, why would I use it? And I would argue that the same way I argued before is that developer experience, the ease of ability to actually use that, for the learning curve for me to actually get started is an imperative function to actually get me started. And if you look at the trend of how Keras and TensorFlow have emerged over the last couple of years, you will see that TensorFlow, which is in blue, and Keras is in red, has been quite effective. And it's very modular, so it allows you to do sequential layers and do multi-layer inputs. And it has the ability to create your layers very easily. And within 3 lines of code, I actually created a neural network. And as a result of that, it's actually quite popular because I can actually just use Keras to do my deep learning pipeline. I don't have to understand the underlying low levels of how it's actually done. There's a third one too, right? And the third one deals with deep learning pipelines and transfer learning, and it's quite appropriate to transfer that to Brooke.
Thank you, Jules. Raise your hand if you've used transfer learning before. All right, I actually want to see every hand in the room go up right now. You use transfer learning on a daily basis. So the idea is that if you want to learn something from scratch, it requires a lot of data and a lot of time. The real life analogy I like to give here is if I'm a baseball player, it's going to be easier for me to pick up tennis or golf than somebody who's never swung a bat before in their life. When you learn these skills, you don't just forget them. That's the motivation for transfer learning. The idea is that if you learn a model for one task, you can take elements of that model and reuse it for another similar task. For example, swinging a bat might not help me with writing code, but it'll sure help me with any racket sport. And so this is a pre-trained neural network. It's taking in an input image, and it's predicting a bunch of different classes. And the lower levels of this neural network learn very generic features. For example, they learn what's a vertical edge, what's a horizontal edge, etc. So the idea behind transfer learning in neural networks is to take a pre-trained model and remove the last few layers, or you use your existing neural network as an initialization for your weights instead of doing random initialization to help you converge more quickly. This way you don't throw away any of the valuable information that you learned in your other task. However, if you have an image classifier, it's not going to help you with your text classification. It has to be on a similar domain. So for example, I could take that same neural network that was classifying it into 1,000 different categories and instead fine-tune this last layer to instead just predict, is this image a cat or a dog? So when do you want to use transfer learning? One of our keynote speakers tomorrow, Andrej Karpathy, has these wonderful notes from his Stanford CS231 class, breaking it down to these 4 different use cases. If your data set is small and similar to the original data set that model was trained on, you might be at risk for overfitting if you try to do any fine-tuning of the last layers. You might just want to retrain that last layer to do your more category-specific task. So instead of predicting 1,000 different categories, if you just want to predict 2, that would be a good use case, but don't try to retrain the rest of the model. If your large data set is similar to the original data set, then you can get away with fine-tuning a few more layers. However, if your new data set's small and vastly different from the original data set, you might just want to start off with a more basic model. For example, try a random forest or linear regression. Whenever you build neural networks, you always want to have some baseline traditional machine learning approach that you can benchmark against. If you can't beat that benchmark, then it's not worth the time to actually build your neural network. Either that or you did something wrong with your neural network. But if your new data is very large and also quite different from your original data set, you could be in a case where you could retrain the model entirely from scratch. In general, most people like to use the initial model weights so that they don't have to relearn those generic features. For example, what's a horizontal edge, what's a vertical edge? You don't need to learn that from scratch. So what and why deep learning pipelines? So what Jules was talking about with TensorFlow and Keras, people typically do on a single machine. They just get a very beefy GPU instance. Instead, deep learning pipelines focuses on applying these concepts across your Spark cluster. So it's open source from Databricks in 2017. We're currently on version 1.0. It integrates very well with Spark MLlib pipelines, TensorFlow and Keras. And if you build a Keras model, you can create a user-defined function, pass it off to your SQL analysts, and they can apply it in SQL. And it's great for transfer learning. So with that, I'm going to go ahead and switch over to our demo. So here, I'm going to start off with using this pre-trained model. This is the VGG16 architecture. So when I talk about model architectures, I'm talking about how many different layers this neural network has, what types of layers, as well as the associated weights. Did any of you attend the Spark meetup last night? Okay, not many, that's okay. Alex from Uber, the creator of HorrorVote, had a wonderful talk about how long it takes to train these models. So the VGG16 model is one of, I think it was actually the second place winner for the ImageNet competition. And these things can take weeks to train to get to convergence. So we don't want to retrain this model from scratch. We're just going to load in the pre-trained weights. So if somebody's already ran this cell before in our cluster, it actually caches the weights. Here we're just running some vanilla Keras code. We're not doing anything distributed right here. And then I'm going to go ahead and define a Python function, which takes in a set of images and my model. It's going to go ahead and resize all the images to be 224 by 224, because that's the input dimensions our VGG16 model expects. Then I'm going to go ahead and predict that image and get the top 3 predictions. Generally, when we do these image classification techniques, if you have to predict many different categories in the ImageNet competition, you have to predict one of 1,000 different categories. If any of your top K predictions are correct, you get that point as being this was a correct prediction. All right, and so we're going to start off with classifying some African and Indian elephants. Go ahead and actually refresh this page. There seems to be some Wi-Fi problems in this room, so I'm actually just going to switch to, I'm going to switch to this pre-run version. So here, I'm going to be predicting African and Indian elephants. Here, when I pass in the African elephant for this first one here, it predicted it with 73% probability. Note these are kind of like pseudo probabilities. They're not true probabilities. All of these sum up to 1, but just don't treat them as true probabilities. Think of them as confidences, if you will. Then if I pass in another example of an African elephant, it confuses it with a tusker, but if we're doing top 5 classification, it got it right. Then we threw in an image of an ox to see if it would get fooled. It predicted bison, but second choice was ox. And then for this last one, of this Indian elephant, it actually predicted poncho. But the second choice was Indian elephant, which is actually quite impressive.
Yeah, because I mean, there's a subtle difference between Indian and African elephants. The African elephants actually have large ears, as actually you see the first one. But look at how he was actually able to discern between the large elephant with big ear and this one with a small one. And it predicted that this was an Indian elephant, despite the fact that he can't really see the ears. But somehow he derived that possibly from the surrounding adornment, that this is something that's very popular in India.
All right, and then part of the motivation for this talk came from Jin Yang's example in Silicon Valley of the hot dog and not hot dog classifier. So we're going to go ahead and throw a few food images here. We're going to start off with the image of this cheeseburger, and it actually picked up as a cheeseburger. There's one layer of cheese, and it discerned this is a cheeseburger over a hamburger. Then we're going to pass in 2 examples of hot dogs, and you can see right off the bat, it does incredibly well, 99.9% confidence that image is a hot dog. No wonder his classifier did well.
So the Silicon Valley, where Jin Yang was right about having that particular hot dog, not hot dog classifier.
And then here we try to see if we could fool our classifier by dressing up a dog as a hot dog. Luckily, it did not get fooled. It predicted different dog types here. Redbone isn't too far off. And then we decided to pass in Jin Yang's image himself. Notably, there's no person category with the ImageNet competition, so instead it picks up on the most prominent most prominent objects within the image. So for this one, it picked up his sunglasses, 44%. And this one, it picked up he's wearing pajamas and a stethoscope, perhaps because of the strings from his hoodie.
But look at actually what he picked up in the background, the bookshop.
Yeah, so this one it picked up bookshop. This looks like a bookshelf back here. All right, and that's great and fun, but that was all running on a single machine. That's just running on the driver. I have this Spark cluster.
Hold on. As of this morning when I ran this, we had just about 2 images. How did he manage to get our founder's image? I mean, this is being recorded, and if it gets classified as dorks or something, we could get into trouble. Did you get the permission?
Ollie used my image earlier today, so I'm using his and the rest of the founders to make it fair.
I like it. Brilliant. Vanity news here. I like to be associated with our founders. Why not?
Yeah, we might be the only 2 with masters and not PhDs, but that's okay.
That's right.
All right, so here we're going to go ahead and switch gears and use the Spark Deep Learning Pipelines library, and we're going to use the Deep Image Predictor. So the difference here is that the VGG16 model is going to be loaded onto each of our workers, and it can do the predictions in parallel. Right now, we're not doing any model training. We're just taking this VGG16 model out of the box, applying it in parallel, getting the top 5 predictions. Let's go ahead and start with your predictions, Jules. Predicts that you're wearing a suit based off of this image, bulletproof vest, and military uniform. And a cute little tie.
I don't look like someone who's a militaristic. I'm more of a saint, and I'm an evangelist. So it's a contradiction over here.
But I think my favorite actually is Matei's predictions. Chainmail. He is our knight in shining armor.
Well, he's the knight of Spark, so that's actually quite appropriate.
Did you know that he's a musician? Accordion, banjo, bassoon, and oboe?
I didn't know that, but I wouldn't be surprised the amount of talent this man has.
But you know, I didn't really like those predictions. Let's go ahead and change the model and use Inception v3.
Why Inception v3?
It's a much more recent
Right.
architecture, and it does much better on the ImageNet competition.
Lovely.
So here it was downloading the model. Let's go ahead and take a look at your predictions, Jules. Ha, even more militaristic. 81% probability.
I'm wearing a bulletproof vest. Does this look like a bulletproof vest to you? There's no bias in there, because my father was in the colonial army, so it could be, I don't know.
Genetic.
Don't want to go there.
But do not fear, Matei's with you now. Military uniform.
Lovely.
But
arms in rise over here for us. Brilliant.
But his hair is so gorgeous, he thinks it's a wig.
That's what I was worried about. Now it's on the recording, so we have to be careful. We better tell Matei that this is something that he's actually wearing. Maybe we should pull his hair and find out if he's really wearing a wig.
Maybe he needs to submit his own model for the ImageNet competition.
All right, lovely. We'll do that too.
All right, and that's all fun and games, but we don't always want those 1,000 categories as output from the ImageNet models. Instead, we might want to do some transfer learning. So you can do things like hot dog or not hot dog. So what we're going to do is we're going to read in some images of cats and dogs, creating a training and test set. And now with Databricks Runtime 4.1, you can actually display images inside of a data frame. And so here, I've set the label of 1 if it's a cat, 0 if it's a dog. I'm not saying cats are better than dogs, it's just binary classification. So we can see our training set's actually quite small. It's 10 images in total. We want to see how well it can discern future cats and dogs, though. And so here, we're going to go ahead and build an MLlib pipeline. This is where Deep Learning Pipelines gets its name. It uses this thing called Deep Image Featurizer, and you pass in the model name. And it simply removes that last layer of the model, which is that ImageNet specific classification. And we're going to go ahead and use that featureized input of our input image as input to a logistic regression model. I could have also picked any MLlib model if I wanted to, decision tree random forest. Train it for 20 iterations. And then I'm going to put both of these inside the stages of my pipeline. That's how it gets the name deep learning pipelines. Then I'm going to go ahead and fit this to our training data. Evaluate the accuracy, 100%. This is great, but our test set also only had 6 images.
Good for demos.
And so now we want to take a look at the raw images that it predicted. So here, the true label was 1 for a cat with probability 92%. But I think what I was most impressed by was this image of a dog. It predicted dog with almost 95% confidence, even though the dog takes up a very small part of this image. And from afar, it's not quite obvious it's a dog. It could also just be a cat on a leash.
Which we do find a lot these days.
Yeah, especially in San Francisco. And now I'm going to transfer it back to Jewel to talk about some takeaways from our presentation.
Okay, since we're actually out of time, I'm just going to run through it. Now, I mean, this is a zoo of what Mate and Ali was talking about. You got all these typical frameworks. What are the things you would actually use? In my opinion, I think Brooke and I agree with that. TensorFlow and Keras definitely seems to be the default choice that people are actually using. Python, would you agree, is one of the commanding language for machine learning and deep learning today?
Definitely, and I definitely see more people using Python 3 than Python 2. Python 2 is end of life in 2020, so definitely make the switch to Python 3. Some things like deep learning pipelines have a dependency that you're running on Python 3.
And the version 2 of this particular presentation is going to include include PyTorch as well, because now you actually have all these languages, all these frameworks written in Python. And then we'll just finish up with Brooke giving you the bubbles of takeaways.
All right, so I recommend using TensorFlow if you want low-level control. For example, if you need direct hardware access, then you might want to consider using TensorFlow. I personally use Keras. I like the high-level declarative API. And then use deep learning pipelines if you want it very integrated with Spark, and if you're doing inference at scale or you want to do limited transfer learning. However, you can also integrate with the machine learning pipelines in Spark if you use Horovode. So I highly recommend checking out the slides from last night's meetup. Horovode is a way of doing distributed model training. So deep learning pipelines is great for distributed model scoring, but if you need to train your model at scale, I recommend using Horovode. It supports both Keras and TensorFlow estimators. And here are a few different resources I recommend going through. Highest recommendation is this course from Fast.ai, and it's entirely free. It's from the old president of Kaggle.
Well, thank you very much. We really don't have any time for any questions because I think we are in overtime. We're going to be at the booth if you have any questions, or just email us, and we'll definitely more than happy to entertain your questions. Thank you all for coming.